Bonding and hybridization. In this lecture, we are going to discuss types of chemical bonds and hybridization. Bonding is the joining of at least two atoms to form a molecule. In 1913, Lewis proposed theories about how atoms combine to form molecules. According to the Lewis model of chemical bonding, atoms bond together in such a way that each atom participating in a bond acquires a valence shell electron configuration of the noble gas which is nearest to it in atomic number. An ionic bond is a chemical bond resulting from the attraction between a positive ion and a negative ion. A covalent bond is a chemical bond resulting from the sharing of electrons between two atoms. A covalent bond can be polar or nonpolar depending on the electronegativities of the atoms bonding together. Electronegativity shows how strongly an atom will attract one or more electrons, forming an octet. If the electronegativity of atoms is the same, the total electron pair is located at the same distance from the nucleus of each atom. Such a bond is called a non-polar covalent bond. If a covalent bond is formed between the atoms with different electronegativities, a shared pair of electrons is shifted to the more electronegative atom. In this case, a chemical bond is called a polar covalent bond. Properties of a covalent bond are expressed through its quantitative characteristics such as energy, length, polarity, and polarizability. If a covalent bond is formed by the pair of electrons of one of the reactant species, it is called a donor-acceptor or a coordination bond. An atom or an ion which gives its electron pair is considered to be a donor, and one that gives a vacant orbital is called an acceptor. A typical example is the formation of an ammonium ion by the reaction of ammonia with a proton. Orbital hybridization. It is known that the electronic structure of the unexcited carbon atom can be expressed by the formula 1s2, 2s2, 2p2. It has two paired with opposite spins s electrons in the second outer electronic shell and only two unpaired p electrons that can participate in the formation of covalent bonds. Therefore, the carbon would have a valence of 2, but it's tetravalent in most of its compounds, and it forms 4 covalent bonds. This is explained by the fact that a pair breaking of the two s electrons occurs at a certain expenditure of energy. One s electron is translated into a vacant orbital of the 2p sublevel, and an atom is converted into an excited state. Where the carbon exhibits a valence of 4 and joins with 4 other atoms with the help of simple or ordinary bonds, the electron density of all 4 valence electrons is redistributed. There is a hybridization of s state and 3 p electron states. Orbital hybridization is a mixing several atomic orbitals of different form and similar energy with the formation of the same number of new hybrid orbitals, whose location in space corresponds to the geometry of the molecule. Hybridization type determines the direction of hybrid orbitals in space and therefore geometry of molecules and ions. How many orbitals hybridize, so much hybrid orbitals are formed. Most importantly, we have sp3, sp2, and sp hybridization. sp3 hybridization results from the combination of the s orbital and all 3 p orbitals in the second energy level of carbon. It results in 4 hybrid orbitals and occurs when a carbon atom is bonded to 4 other atoms. The geometric arrangement of those 4 hybrid orbitals is called tetrahedral. Another kind of hybridization uses s orbital and 2 p orbitals from the second energy level of the carbon to form 3 hybrid orbitals. This kind of hybridization is called sp2 hybridization. It has 3 hybrid orbitals and there is also an unchanged p orbital. The geometric arrangement of these 3 sp2 hybrid orbitals is in a flat plane with 120 degrees angles between them. This kind of hybridization occurs when a carbon atom is bonded to 3 other atoms. It is a very simple molecule with just the carbon atom and the other 3 atoms. It will be a flat triangular molecule. If it is a part of a larger molecule, this part will have a flat triangular shape. There is a third type of hybridization. It is called sp hybridization. The s orbital and one of the p orbitals from the carbon second energy level are combined together to make 2 hybrid orbitals. Those hybrid orbitals form a straight line. There is a 180-degree angle between one orbital and the other orbital. sp hybridization only uses one of the p orbitals. There are still 2 p orbitals left. These p orbitals are at right angles to one another and to the line formed by the hybrid orbitals. This kind of hybridization occurs when a carbon atom is bonded to 2 other atoms. A single covalent bond formed due to the overlap of orbitals of the 2 atoms along the line joining the 2 nuclei orbital axis is called a sigma bond. A sigma bond can occur when any atomic orbitals s, p, and hybrid overlap. The length of the carbon-carbon single bond is 0.154 nanometers. Multiple bonding. Ethylene is an example of a carbon compound with sp2 hybridization. A double bond is a combination of 1 sigma bond and 1 pi bond. The bond formed by side overlapping, non-hybridized p atomic orbitals with a maximum overlap on both sides of the line joining the nuclei of atoms is called a pi bond. An sp hybridized carbon forms a triple bond. Acetylene is an example of a compound with a triple bond. Both carbons in acetylene are sp hybridized. A triple bond is formed by 3 pairs of shared electrons. The state of these pairs of electrons is not identical. A triple bond consists of 1 sigma and 2 pi bonds. In acetylene, the HCC bond angle is 180 degrees and it has a linear shape.